This video is engaging with how machine learning is used for dynamic system order reduction. Machine learning is revolutionizing how we simulate dynamic systems, faster, smarter, and more efficient than ever. Dynamic system reduction is the process of simplifying complex systems while maintaining their essential behaviors. This is crucial when dealing with large-scale systems in fields like mechanics, electrical engineering, and fluid dynamics. Welcome to the future of order reduction, where data-driven intelligence meets mechanical engineering. What is order reduction? Dynamic systems, like buildings under earthquakes or turbines in motion, are complex and computationally demanding. Order reduction simplifies these models, capturing essential behavior while slashing computational cost. Why does this matter? Because it enables real-time control, faster design iterations, and insight into systems previously too complex to simulate efficiently. Traditional versus machine learning approaches. Traditional techniques, like modal analysis and balanced truncation, work well for linear systems, but struggle with nonlinear, high-dimensional problems. That's where machine learning shines. It learns from simulation or sensor data, handles nonlinearity with ease, and compresses large systems using techniques like autoencoders or PCA. ML-based workflow. Here's how it works. Data collection. Simulate or measure system behavior under various conditions. Feature extraction. Identify dominant patterns using PCA. Model training. Use neural networks to learn reduced dynamics. Validation. Ensure accuracy before deployment in design or control tasks. Real-world example. Building vibration analysis. Imagine simulating a skyscraper's seismic response, hundreds of degrees of freedom. Using ML, we reduce this to key vibration modes, train a model, and predict behavior in seconds instead of hours, with accuracy nearly identical to full-scale simulations. Industry applications for dynamic system order reduction. Across industries, ML-based reduction is unlocking new possibilities like in aerospace, predicting aeroelastic flutter faster for safer aircraft design. Automotive, speeding up crash simulations and improving thermal management. Energy, modeling combustion in turbines and optimizing wind turbine performance. Challenges to consider, of course. ML has challenges. Requires quality data. Can act like a black box. Struggles with unseen scenarios. But hybrid approaches, combining physics with data, are already addressing these concerns. Let's summarize. Machine learning isn't replacing physics, it's enhancing it. By reducing complex systems to their core dynamics, we can simulate faster, optimize smarter, and build more resilient, efficient technology. This is the future of engineering, where simulation meets intelligence. Smarter simulations, real-time decisions, scalable innovation.